Good morning, students. Wishing that you all are well. And last class we have two assignments about two scientists, Kanada and Amedeo Avogadro, and today we are going to discuss about Kanada. Kanada, who lived between 6th and 4th century BCE, he is an Indian philosopher, natural scientist and philosopher, and his notable idea is atomism. And what is interesting is behind his name that Kana means atom and Ada means ether. He proposed everything can be subdivided and this subdivision cannot go on forever. There must be the smallest particle, and he named it as paramanus. Paramanus means atoms. These atoms are the indestructible particles of matter, and this is indivisible because it is in a state at which no measurements can be attributed. And he gave invariance arguments to determine the measurements of atoms and proposed there are four kinds of atoms. Four kinds of atoms. Atoms of the same substance combined form diatomic and triatomic molecules, and they differ both qualitatively and quantitatively. And there are two states of atoms, state of rest and state of motion. State of rest and motion. But this is against the Greek school of thought, that they proposed that atom can only differ quantitatively and there is only one kind of atom. And after many centuries there came atomic theory of Dalton put forward by John Dalton in 18th century. And you need to Google through, or you need to collect the information about or the comparison between the proposals made by John Dalton in 18th century and by Kanada at between 6th and 4th century BCE. That's your first assignment. And now you are going to solubility. Solubility. What is solubility? And what happens when a solute dissolves in a solvent? Dissolution, the process dissolution takes place. And what's this dissolution? Making of an intermolecular bond between the solute and the solvent molecule is simply known as dissolution. And there is a new word came, that's intermolecular forces. These are the repulsive or attractive forces arises between two reacting entities when it come close to each other. And it is entirely different from covalent bonds. And these properties of these intermolecular forces are first studied by a Dutch scientist Johannes van der Waals, and these forces become van der Waals forces. Johannes van der Waals. And there are different reacting entities and their electronic environment is different. There are many kinds of intermolecular forces. First we are considering dispersion forces or London forces, how it arises between two non-polar molecules. For this we are going to take two non-polar molecules, two noble gas atoms, say A and B. These are non-polar noble gas atoms. These also non-polar. You know, for a noble gas atom, the electronic environment is symmetrical around the nucleus, and there is no, the electron density is symmetrically distributed around the atom. There is the polarity is zero. But you think that at a fraction of a second the electronic environment changes. what happens is that the electron density is accumulating towards one of the side. What happens to the atom? The electron density, we can draw this as, it is distorted like this, and electron density is accumulating here. There is a charge accumulation at one of the terminal and an opposite charge here. You can say that this is the arisal of an instantaneous dipole. Instantaneous dipole. And what about this atom? Atom B, when it comes close to this atom, its electronic environment also distorted because of the instantaneous dipole. It is an opposite charge is inducing here and a negative charge here. This is an induced dipole. There is an instantaneous induced dipole interaction between these two because of these opposite charges. There is an attractive force, intermolecular force. This is known as dispersion force. This is the first type of force which arises between two non-polar atoms. How it changes, we are going to take a look. And the first is dispersion force. Dispersion force, or otherwise it is known as London force. London force, by the scientist who first studied is Fritz London from Germany. And if the two atoms are polar, dipole interactions are possible. Dipole forces are possible there. And if one of the molecules is a polar one and the second is a non-polar, there arises induced dipole interactions, forces. And if the molecule contains hydrogen atom, one of the molecule contain hydrogen atom, one of the entity contain hydrogen atom, and the other an electronegative atom, hydrogen bonding is possible. Hydrogen bonding is possible. These are the kinds of forces, intermolecular forces, arises between reacting entities. And how it come into play in solutions or during the process dissolution, we are going to take a look. What is solubility? When we are adding a solute to a solvent molecule, what happens? The process dissolution takes place. The term is dissolution. How it take place? We are taking a system like this. We can take a system like this. And this is the solvent interface. And these are the solvent molecules throughout the medium. And these are the solute molecule we are introducing towards the medium. Then when a solute molecule entering into this one, we are getting solute molecule in this medium also. And if there is the above mentioned possibility of making an intermolecular bond between these two, we can make a solute-solvent intermolecular force. And a perfect solution is obtained. How can we depict this is as an equation? Solvent plus solute, solution. When solvent plus solute undergoes dissolution, we are getting a solution. So the forward process here is dissolution. Dissolution is going on, take place. We are introducing more and more solute particles here, and the concentration of solute molecule is going on increasing. What happens at a particular time? After a particular time, what happens? Some of the solute molecule from the solution site get collide with the pure solute molecules and get converted into solute molecules. And this is the reverse process of dissolution, and this process is known as crystallization. This is known as crystallization. You know that after time, the rate of dissolution and the rate of crystallization is the same, and there gets a dynamic equilibrium. At a dynamic equilibrium, what happens is that the concentration of solution is maximum in this solution, and this particular concentration is known as solubility. Then what is solubility? The maximum concentration of solute in a solution. Otherwise, we can say that the concentration of solute at equilibrium is known as solubility. It is known as solubility. Good. And it's only a concentration term. Beyond that, we cannot increase the concentration of solute in that solution. And every system, there are many factors that influence it. For this solution, what are the factors influencing solubility? How we can increase the concentration, how we can decrease the concentration, we are going to take a look. Factors affecting solubility. Factors. The first, nature of solvent and solute. So for that, first we are considering two systems. One is sodium chloride plus water system, and the second one is sodium chloride benzene system. What's the difference between these two? Here the solute is sodium chloride and the solvent is water. You know that there is the possibility of making a hydrogen bond or making the same intermolecular, they present the same intermolecular forces, and there is the possibility of making an intermolecular force, or a solution is possible in this case, and solution is possible. And what about this system? Sodium chloride and benzene, no possibility of such intermolecular forces, therefore no solution is from this system. So we can say that for a system, the components need the same intermolecular forces. So we can say that like molecules should be present there for the preparation of a solution. So we can write it as like dissolves, like. This is the first factor. And the second factor is temperature. What about temperature? What about the system you are under consideration? There are two types of reactions are there. One is endothermic reaction, the other is exothermic reaction. Endothermic and exothermic. What's the difference between these two? In an endothermic reaction, if you are considering the forward reaction, that means dissolution. If it is endothermic, that means that process absorbing heat from the system. What we are adding heat to that system, the system will absorb heat and dissolution rate increases. That means for an endothermic process, if temperature increases, the rate of dissolution also increases. And for an exothermic process, that means a heat liberating process. If dissolution is a heat liberating process, if you are adding temperature to the system, the rate of exothermic reaction or the rate of dissolution decreases because of the increase of the reverse process. These are according to Le Chatelier's principle. To undo the effect, the system will do the process that opposite to the process we are doing in that system. That is Le Chatelier's principle. And these are the effect of temperature. Then the third one is pressure. For most of the solid solutions and liquid solutions, some of the liquid solutions, there is no significant effect for pressure because of the incompressibility of solids and liquids. But in gaseous solutions and the gas in liquid solutions, there is significant effect for pressure because gases have high rate of compressibility. So pressure have a significant effect on gaseous solutions, on gases, particularly gases as a component. Now we are going to classify the solutions into three and going to study about that. Solutions are classified into solid solutions, liquid solutions, and gaseous solutions. And again, the solid solutions, you know that almost all the alloys and some of the gases absorbed in solid are under this category, is again classified into substitutional and interstitial. Substitutional and interstitial. Now, what is this substitutional solid solution? Now consider a crystal lattice of the solid. This is the solvent crystal lattice, and atoms are arranged like this. Atoms are arranged in a crystal lattice like this, and this is the solvent atoms. If some of the solvent atoms are replaced by the solute atoms, and here we are replacing this atom with a solute atom, and we can replace some of the atoms here, we are getting a substitutional solid solution. For example, steel, bronze, brass, etc. And if you are taking steel, you know that it is formed from iron and carbon. Some of the carbon atoms came here instead of iron atoms. You are getting a substitutional solid solution. And what is interstitial solid solution? For interstitial solid solution, if you are taking a solvent lattice like this, again we are arranging the atoms in it like this. We are going to arrange the atoms like this, and what they present is voids. Because of the Bravis lattice arrangement, we are getting two types of voids. We already studied that. There is the tetrahedral voids and octahedral voids. If it is a face-centered cube or a structure, there get tetrahedral voids, and in these voids, some of the solute atoms are placed, and we are getting interstices. The atoms are placed in the interstices of the solvent crystal lattice. We are getting what? Interstitial solid solutions. A good example of this is tungsten carbide. That is WC. Tungsten is forming a face-centered cubic lattice, and it has an octahedral void. And in octahedral void, this carbon atom is coming, and what happens is that around the carbon atom there is 6 tungsten atoms because of the face-centered cubic lattice. This is another type of what? Interstitial solid solutions. And the other type of interstitial solids are some of the metals like palladium and platinum can absorb some hydrogen gases are there. That is gases in solid solutions. That's also coming under interstitial solutions. And liquid solutions are of 3 types. That means liquid is the solvent, and solid in liquid, liquid in liquid, and gas in liquid solutions. And this is important because we are going to look the binary solutions in liquid solutions, including Henry's law and Raoult's law, and including ideal and non-ideal solutions. So these are the liquid solutions. And gaseous solutions, you know that air is a good example of that. Any mixture of air, including the tanks of scuba divers, you already studied that helium, nitrogen and oxygen are mixed, and all type of mixtures of air are examples of gaseous solutions. These gaseous solutions and gases and liquids pressure has a main role in it. So we are going to take a look of these binary systems mainly in the next class. And today, this is to the last segment of this class. We are going for the assignments, next class assignments. 2 scientists also, and one is the same. Do you know that it is an ancient scientist? Now we are going to look the ancient scientist and comparison of these two. One is the ancient Indian scientist, and it is pronouncing as Vagpata. The first scientist is Vagpata. He is from 12th century AD. And for his proposal, he made a very good contribution to laboratory and layout of laboratory. And you are Google through this one, Vagpata. And our second scientist is we just studied about van der Waals forces, and therefore our second scientist is Johannes van der Waals. Johannes van der Waals. He is a Dutch scientist. These are our 2 assignments. We are coming with these assignments and with binary liquid solutions, Raoult's law, Henry's law, and ideal and non-ideal solutions.